Chapter 1. What is observability? Observability is not just another word for monitoring. It's a measure of how well you can understand any state your system can get into, no matter how new or strange, without needing to ship new code to understand it. The concept originated in control theory, but for software, it's about being able to ask open-ended questions about your application's inner workings by only observing its external outputs, its telemetry. If your system is truly observable, you can answer questions like, which specific users are experiencing timeouts right now, and what do their requests have in common? Which of our top 100 most active customers just started causing a performance issue in the last hour? This capability is essential for modern systems, microservices, cloud-native apps, because their complexity makes it impossible to predict all potential failure modes in advance. Traditional monitoring, which relies on pre-configured dashboards and alerts for known failure types, falls short. Observability is enabled by collecting telemetry with high cardinality, many unique values like user IDs or request IDs, and high dimensionality, many attributes or fields per event. This rich, granular data is what allows you to slice and dice your way to the root cause of any problem, known or unknown. Chapter 2. How debugging practices differ between observability and monitoring. This chapter contrasts the old way of debugging with the new. The monitoring way, reactive and intuitive. How it works? An alert fires. An engineer looks at a pre-built dashboard. They use their past experience and intuition to guess the cause. The message queue graph looks weird. It's probably that again. They then look for data to confirm their hunch. The problem? This approach relies heavily on institutional knowledge. The best debugger is often the person who's been there the longest. It's ineffective for novel, unknown problems because you can't have a dashboard for something you've never seen before. The observability way, proactive and exploratory. How it works? An issue is detected, perhaps via an SLO, see Chapter 12. An engineer starts with a broad question and follows the data. They use the tool to slice and dice across many dimensions, forming hypotheses and iteratively narrowing down the problem. Anyone can follow the breadcrumbs to find the answer. Chapter 3. Lessons from Scaling Without Observability. This chapter is a real-world case study from co-author Charity Major's time at Parse, a mobile backend-as-a-service platform. The story illustrates the painful transition from a world where traditional monitoring worked to one where it catastrophically failed. The challenge. Parse was a multi-tenant platform, meaning thousands of different apps ran on their shared infrastructure. The workload was completely unpredictable. A single customer's app, like a Norwegian death metal band's live stream, could suddenly spike and take down the entire platform. The breaking point. Traditional tools like Nagios and Ganglia were useless. They showed that everything was slow, but couldn't pinpoint why. Creating a custom dashboard for every new problematic app was not scalable. The team realized they were constantly facing novel failure modes they couldn't predict. The aha moment. After being acquired by Facebook, the team was exposed to Scuba, an internal tool that allowed them to slice and dice high cardinality data in real time. Suddenly, they could investigate novel problems by following the data, dropping the time to find root causes from days to minutes. The lesson. This experience was the genesis of Honeycomb. It proved that for modern, complex, and unpredictable systems, you must move from pattern-matching known failures to having the tools to explore unknown unknowns. Chapter 4. How Observability Relates to DevOps, SRE, and Cloud Native. This chapter connects observability to other modern software movements. Key idea. DevOps, SRE, and Cloud Native are philosophies and technologies that enable teams to build and ship software faster and more reliably. However, they do so by creating more complex, distributed, and dynamic systems. The problem they create. When you break a monolith into microservices, you lose the ability to use a simple debugger. When your infrastructure is ephemeral, containers spinning up and down, you can't just SSH into a box to see what's wrong. This increased complexity creates a critical need for a new way to understand system behavior. The solution they require. Observability is the practice that makes these modern systems manageable. The Cloud Native Computing Foundation, CNCF, even includes observability as a core tenet of cloud-native systems. How observability empowers them. Observability is the engine that powers advanced DevOps and SRE practices. You can't do effective chaos engineering, implement meaningful SLOs, or conduct blameless postmortems without the deep, contextual data that observability provides. Chapter 5. Structured events are the building blocks of observability. This chapter identifies the fundamental data primitive required for observability. Key idea. The core building block of observability is the arbitrarily wide structured event. What it is, think of it as a single rich JSON blob that captures the full context of one unit of work, for example, a single incoming request to one of your services. As the request is processed, you add key value pairs to this blob: the user ID, the endpoint being hit, the duration, parameters, database query details, feature flags, etc. When the request is done, you send this single wide event to your observability tool. Why not metrics? Metrics are pre-aggregated numbers. HTTP requests total loses the context of each individual request. You can't go back and ask new questions about data that's already been boiled down to a single number. Why not traditional logs? Unstructured logs, user X logged in, are for humans to read, not for machines to analyze. While structured logs are better, they often represent fragments of an event rather than the whole context in one place. To achieve observability, your telemetry must be based on these rich, queryable events. They must support high cardinality and high dimensionality data so you can ask any question you want later. Chapter 6. Stitching Events into Traces. This chapter demystifies one of the most important concepts in observability: distributed tracing. Key idea. A distributed trace is nothing more than a collection of structured events that have been stitched together. A single user request might travel through multiple services, e.g., API gateway, auth service, billing service. Each of those stops generates its own event, called a span. A trace connects these spans to show the full end-to-end journey of the request. This is accomplished using a few key pieces of data that are passed from one service to the next, usually in HTTP headers. 1. Trace ID, a unique ID for the entire end-to-end request. Every span in the trace shares this ID. 2. Span ID, a unique ID for the work done in a single service. 3. Parent ID, the span ID of the service that called the current one. By passing these IDs along, you can reconstruct the entire request path and visualize it as a waterfall diagram, making it easy to spot bottlenecks. The real power comes from adding rich, custom context to each span, allowing you to debug not just the timing, but the business logic at each step. Chapter 7. Instrumentation with OpenTelemetry. This chapter covers the how-to of generating the events and traces your application needs. Key idea. Instrumentation is the process of adding code to your application to emit telemetry. The modern, vendor-neutral way to do this is with OpenTelemetry, OTel. The old way. In the past, you would use a proprietary agent or library from your monitoring vendor. If you wanted to switch vendors, you had to re-instrument your entire application. This created vendor lock-in. The OTel way. OTel is an open-source standard. You instrument your code once using the OTel libraries. Then you can configure an exporter to send that data to any backend you choose: Honeycomb, Datadog, Jaeger, etc. This gives you freedom and flexibility. The book recommends a two-step approach to instrumentation. 1. Start with auto instrumentation. OTel provides automatic instrumentation for popular frameworks, e.g., HTTP servers, gRPC clients, database drivers. This gives you a basic trace for every request with minimal effort. 2. Add custom instrumentation. This is where you get the most value. Manually add attributes and create custom spans in your code that are specific to your business logic. For example, add the cart ID or feature flag status to a span. This is what allows you to debug your actual application, not just the framework. Chapter 8. Analyzing events to achieve observability. This chapter describes the human workflow for debugging with observability data. Key idea: observability enables a scientific, hypothesis-driven debugging method called the core analysis loop. This contrasts with the traditional method of debugging from known conditions, where you rely on past experience and intuition. Debugging from first principles with the core analysis loop works like this. 1. Start with the problem. You notice a spike in latency on a graph. 2. Visualize and isolate. Highlight the group of slow events in your observability tool. 3. Search for commonality, the bubble up. This is the key step. The tool should be able to automatically compare the thousands of attributes on the slow events to the attributes on the normal events. It then bubbles up the dimensions that are most different. For example, it might show you app.version.2.1.4 is present in 100% of slow events, but only 2% of normal events. User.plan.enterprise is present in 98% of slow events, but only 10% of normal events. 4. Form a hypothesis and refine. From this, you form a hypothesis. It seems like the problem is affecting enterprise users on the new v2.1.4 release. You then filter your view to just those events and repeat the loop, digging deeper until you find the root cause. This methodical process, especially when the tool automates the comparison step, is what allows any curious engineer, not just the expert, to solve complex, novel problems quickly. Chapter 9. How Observability and Monitoring Come Together. This chapter clarifies that observability doesn't make monitoring obsolete. They are complementary tools for different jobs. A simple guideline. Monitoring is for systems. Use traditional monitoring, metrics, dashboards, alerts for your underlying infrastructure, things that are predictable, change slowly, and have known failure modes. Think CPU, memory, disk space, or the health of a Kafka cluster. This is for the known unknowns. Observability is for software. Use observability, wide events, traces, exploration for your application code, the code you write that delivers business value. This code is complex, changes constantly, and fails in unpredictable ways. This is for the unknown unknowns. An organization's needs for each will vary. A company that runs its own data centers will need a lot of system monitoring. A company that is all in on serverless and PaaS will need very little system monitoring, but will rely heavily on observability to understand their application logic. The two worlds meet when you need to correlate application behavior with system constraints. For example, you might add key infrastructure metrics like CPU usage as attributes to your observability events so you can see everything in one place. Chapter 10. Applying observability practices in your team. This chapter provides practical advice for getting an observability initiative off the ground. Start with the biggest pain points. Don't start with a simple, stable service to prove it out. You won't see any value. Instead, pick the most complex, painful, and mysterious service that is constantly causing outages. Solving a hard problem quickly is the best way to demonstrate the value of observability and win supporters. Buy instead of build initially. Your goal is to prove value fast, not spend 6 months building your own custom tooling. Use a commercial or mature open source solution to get started. Use OpenTelemetry for your instrumentation so you aren't locked in. Flesh out instrumentation iteratively. Start with auto instrumentation. Then, every time there's an incident or a tricky bug, make it a practice to add the custom instrumentation that would have made the problem easy to find. Your instrumentation will grow organically to cover what matters. Leverage existing efforts. Make the transition easier by pulling data from your old systems into the new one. For example, you can configure Logstash to fork your logs to your new observability tool, allowing teams to compare the experience. Prepare for the hardest last push. Getting the first 80% of your services instrumented is often driven by solving active pain. The last 20%, often in older, less touched services, can be a slog. Plan a dedicated effort, like a hack week, to get the project over the finish line. Chapter 11, Observability-Driven Development. This chapter advocates for shifting observability left and making it part of the development process, not just an operational one. Observability-Driven Development, ODD, is presented as a complement to Test-Driven Development, TDD. TDD validates that your code works correctly against a known specification in a controlled, isolated environment. ODD validates that your code behaves as expected in the messy, chaotic, and unpredictable environment of production. The core practice of ODD is for a developer to ask themselves with every pull request, how will I know if this change is working correctly in production? The answer is to ship the necessary instrumentation along with the feature code. When engineers own their code in production, meaning they are the ones who watch it deploy and are on the hook if it breaks, they are naturally motivated to add good instrumentation. This creates a tight feedback loop that is essential for building quality code. ODD empowers developers to treat production not as a scary glass castle to be avoided, but as an interactive playground where they can see the real-world impact of their work. Chapter 12, Using Service-Level Objectives for Reliability. This chapter introduces a modern, more effective way to think about alerting. The problem with traditional alerting. Most alerts are based on potential causes, e.g., CPU utilization is over 90%. These are noisy, often not actionable, and don't correlate well with actual user impact. This leads to alert fatigue, where engineers learn to ignore alerts. A better way, service-level objectives. An SLO is a target for how reliable a service should be, measured from the user's perspective. It's built on a service-level indicator, SLI, which is a simple rule that defines whether a given event was good or bad. Example SLI. A request to the home page is good if it returns a 200 status code in under 200 milliseconds. Example SLO. 99.9% of homepage requests over the last 30 days must be good. This approach has a key advantage. It decouples the what from the why. The SLO alert tells you what is happening. User experience is degrading. This is the only thing that should wake someone up in the middle of the night. Observability tools are then used to figure out why it's happening. This focus on user-impacting symptoms drastically reduces alert noise and makes every alert meaningful and actionable. Chapter 13, Acting on and Debugging SLO-Based Alerts. This chapter dives into the mechanics of how to make SLO-based alerts work in practice. Key concept, the error budget. An SLO of 99.9% availability means you have an error budget of 0.1%. This is the percentage of bad events you are allowed to have over your time window, typically a 30-day sliding window, before you violate your SLO. Error budget burn alerts. The goal isn't to alert when your budget hits zero. By then, it's too late. The goal is to alert when you are burning through your budget at a rate that will cause you to exhaust it before the end of the window. This is a forecasting problem. A burn alert looks at the rate of errors in a recent baseline window, e.g. the last hour, and projects it forward into a look-ahead window, e.g. the next 4 hours. A fast burn, e.g., at this rate, we'll burn our whole month's budget in 2 hours, is an urgent alert that requires an immediate response. A slow burn, e.g., at this rate, we'll burn our budget in 25 days, is a non-urgent notification that can be addressed during business hours. The chapter also argues that using raw event data for SLO calculations is far more accurate and provides a better signal than using pre-aggregated time series data, metrics. Chapter 14, Observability and the Software Supply Chain. This guest chapter from engineers at Slack expands the application of observability beyond production systems to the software supply chain, the CI/CD pipelines, build systems, and testing infrastructure that developers use every day. Key idea: for the teams that maintain them, CI/CD systems are their production workload, and they suffer from the same kinds of complex, distributed systems problems. Slack's CI system is a massive, multi-stage, distributed application. When a developer complains that tests are flaky or builds are slow, it's a classic unknown debugging problem. The root cause could be in the test code, the build agent, the underlying host, a networked service, or a dozen other places. By instrumenting every stage of their CI pipeline with distributed tracing, the Slack team was able to create a shared set of dimensions, e.g., commit ID, test suite name, Jenkins worker label, that provided context across the entire workflow. Quickly identify the root causes of slowness and flakiness, which were often related to infrastructure or configuration issues, not just bad test code. Embed actionable alerts directly into Slack with links to pre-filtered observability queries to help developers and platform teams triage issues faster. Chapter 15, Build versus Buy and Return on Investment. This chapter tackles the critical strategic decision of whether to build an in-house observability solution or buy a commercial one. The book argues that this is a false dichotomy. The best approach for most organizations is buy and build. The true cost of building. Building your own solution from open-source components is never free. The hidden costs include the hardware, cloud infrastructure to run it, and, more importantly, the opportunity cost of the highly paid engineers who must maintain it instead of working on your core product. This almost always ends up being more expensive than a commercial tool. The risks of building. It is incredibly difficult to build a tool with a good user experience that gets wide adoption. In-house tools often stagnate and fall behind the state of the art. The costs and risks of buying. The sticker price of commercial tools can be high, and some vendors use pricing models that penalize you for asking more questions, e.g., per query or per seat pricing. There's also the risk of vendor lock-in if you use their proprietary instrumentation. The recommended buy and build strategy. The optimal path is to buy a flexible, extensible commercial platform that has a powerful API. Then have a small internal observability team that builds on top of it. This team doesn't build the core storage engine. Instead, they build custom integrations, client libraries, and abstractions that make the tool perfectly suited to your organization's specific needs. This gives you the best of both worlds. You leverage a best-in-class core platform while still getting a tailored solution. Chapter 16, Efficient Data Storage. This chapter, a deep dive into data storage architecture, explains what it takes to build a backend that can power a true observability workload at scale. The challenge. An observability data store has incredibly demanding requirements. It must handle a very high write throughput. It must return queries over billions of rows in seconds. It must support ad hoc queries on high cardinality, high dimensionality data without requiring you to predefine indexes. Why traditional databases fail. Time series databases, TSDBs, are built for low cardinality metrics. They suffer from cardinality explosion when you try to use them for rich event data. General-purpose NoSQL databases or search indexes, like Elasticsearch, are often too slow for the types of arbitrary analytical queries that observability requires. A viable architecture, using Honeycomb's retriever as a case study. The book outlines a hybrid columnar store partitioned by time. Columnar storage. Instead of storing data by row, you store it by column. When a query only needs 3 out of 500 columns, you only have to read those 3 files, making it dramatically faster. Time partitioning. Data is broken into immutable time-based chunks. Example, 1-hour segments. Queries only need to scan the segments that overlap with their time range. Affordability with tiering. Recent, hot data is kept on fast, expensive storage, SSDs. Older, cold data is moved to cheaper object storage, like AWS S3. Speed with parallelism. The query engine uses a map-reduce model, often with serverless functions, like AWS Lambda, to scan many cold data segments in parallel, making queries over long time ranges just as fast as recent ones. Affordability with tiering. Recent, hot data is kept on fast, expensive storage, SSDs. Older, cold data is moved to cheaper object storage, like AWS S3. Speed with parallelism. The query engine uses a map-reduce model, often with serverless functions, like AWS Lambda, to scan many cold data segments in parallel, making queries over long time ranges just as fast as recent ones. Chapter 17. Cheap and accurate enough, sampling. This chapter addresses the reality that, at massive scale, collecting and storing 100% of your telemetry data is often cost-prohibitive. Sampling is the solution. Key idea: smart sampling allows you to drastically reduce data volume while retaining the high-fidelity signal you need for debugging. It's fundamentally different from aggregation, metrics, because it keeps the full, rich context of the events it selects. The chapter details a progression of sampling strategies. 1. Fixed-rate sampling, the simplest approach, e.g., keep 1 in every 100 events. It's easy to implement, but can easily miss rare but important events like errors. 2. Dynamic or target rate sampling, adjusts the sampling rate based on traffic volume. If traffic spikes, the rate goes down to maintain a predictable ingest volume. 3. Content-based or key-based sampling. This is the most powerful technique. You sample different types of events at different rates based on a key. Example, you could define a key based on the customer ID and the HTTP status code. Then you can set a rule. For customer A, keep 100% of events with a 500 status, but only 1% of events with a 200 status. The chapter also explains the difference between head-based sampling. The decision to keep or drop a trace is made at the very beginning of the request. It's simple, but you might drop a trace that later turns out to have an error. Tail-based sampling. All spans for a trace are collected and buffered. The sampling decision is made after the entire trace is complete. This allows you to say, keep 100% of traces that contain an error, which is incredibly powerful, but more complex to implement. A sophisticated sampling strategy combines these techniques to provide the best signal for the lowest cost. Chapter 18. Telemetry Management with Pipelines. This guest chapter from engineers at Slack introduces the concept of a telemetry pipeline, a critical piece of infrastructure for managing observability at scale. Key idea: a telemetry pipeline is a dedicated service that sits between all of your instrumented applications, the producers, and your various backend systems, the consumers. Instead of having every application send data directly to Datadog or Splunk, they all send it to the pipeline, which then handles the routing, processing, and management. A mature telemetry pipeline performs several key functions. Routing intelligently sends different data to different places. E.g., traces go to Honeycomb, security logs go to an archival system, metrics go to Prometheus. Buffering uses a message queue like Kafka to smooth out traffic spikes and prevent data loss. Enrichment adds common metadata to all events, e.g., the AWS region or K8's pod name. Filtering and redaction strips sensitive data, PII, before it reaches a backend or drops low-value, noisy events. Transformation converts telemetry from one format to another, e.g., converting incoming Zipkin formatted traces into OpenTelemetry format. Capacity management centrally manages sampling and rate limiting rules. Using a centralized pipeline abstracts this complexity away from application developers, providing a consistent and reliable way to handle telemetry across a large organization. Chapter 19. The Business Case for Observability. This chapter provides the arguments needed to justify an observability initiative to business leaders. Key idea: adopting observability is not just a technical decision, it's a business decision with a clear return on investment. The chapter outlines two paths to adoption. 1. The reactive path. This often happens after a major, painful outage where traditional tools failed or when developer toil and burnout become unsustainable. 2. The proactive path. This involves making a business case based on the expected ROI. The key business benefits of observability are: higher revenue. Improved uptime and performance directly lead to better customer experience and fewer abandoned transactions. Cost savings from faster incident response. Reducing mean time to resolve means fewer engineering hours are wasted on firefighting. Cost savings from avoided incidents. Observability helps teams find and fix problems proactively before they become major outages. Cost savings from decreased employee churn. Reducing toil and the stress of on-call leads to happier, more engaged, and more productive engineers who are less likely to leave. The chapter provides guidance on how to know when you have enough observability, when it becomes a natural part of the development workflow and teams are confidently shipping high-quality code. Chapter 20. Observability Stakeholders and Allies. This chapter argues that the value of observability data extends far beyond the engineering team. Key idea: to spread a culture of observability, you should democratize access to the data and create allies in other parts of the business. Your observability data is a real-time treasure trove of information about how customers are using your product. This is valuable too. Customer support. They can look up a specific customer's trace to verify a reported issue in real time, instead of asking, "Can you send me a screenshot?" This leads to faster, more effective support. Product teams. They can get quantitative, real-time data on feature adoption. Are customers using the new feature we just shipped? How are they using it? Which users are abandoning it and why? Customer success. They can proactively identify which customers are struggling with a feature or are still using a feature that is about to be deprecated. Sales and executives. They can get data on which features are most heavily used by high-value customers, informing strategic decisions and sales conversations. While these teams might also use a traditional business intelligence (BI) tool, observability data is different. It's optimized for real-time speed, ad hoc exploration, and high cardinality engineering data, whereas BI is optimized for long-term, structured business reporting. Giving these teams access to observability data creates a shared understanding of the customer experience across the entire organization. Chapter 21. An Observability Maturity Model. This chapter introduces a framework to help organizations benchmark their observability practice and plan their adoption journey. The Observability Maturity Model, OMM, is not a rigid scorecard, but a guide to help teams identify areas for improvement. It's based on the idea that high-performing teams demonstrate maturity across 5 key capabilities. For each capability, the model describes what it looks like to be doing poorly versus doing well. The 5 capabilities. 1. Respond to system failure with resilience, moving from frequent, stressful, all-hands-on-deck incidents to calm, efficient, and effective responses where on-call is sustainable. 2. Deliver high-quality code, defining quality by how code actually behaves in production and how easily it can be debugged and maintained. 3. Manage complexity and technical debt, using visibility to make informed decisions about where to invest engineering effort, preventing parts of the system from becoming a haunted graveyard that no one dares to touch. 4. Release on a predictable cadence, gaining the confidence to ship changes frequently and safely, knowing you can quickly understand the impact of any deployment. 5. Understand user behavior, empowering product and business teams to use real-time data to understand feature adoption and user experience, leading to better product decisions. An organization can use this model to assess where they are on their journey and to prioritize which capability to focus on next. Chapter 22: Where to go from here. The final chapter offers a refined definition of observability based on all the concepts in the book, reflects on the rapid evolution of the field, and makes predictions for the future. The refined definition. You have observability if you can understand any state of your software system by arbitrarily slicing and dicing high cardinality and high dimensionality telemetry data, using the core analysis loop to quickly isolate the source of issues without needing to predict those issues in advance. Predictions for the future. OpenTelemetry will be ubiquitous. It will become the unquestioned standard for all instrumentation. Observability will conquer the front end. It will become the primary way to understand browser and mobile applications, replacing traditional real user monitoring, RUM, and synthetic monitoring tools by combining the best of both. Custom instrumentation will be standard practice. Just as code must have comments and tests, it will be expected to have rich, custom instrumentation. The biggest evolution will be in developer workflows. The loop between writing code and seeing its real-world impact in production will continue to shrink, making developers faster, more confident, and more connected to their users. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe. And join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.